Our next speaker is Sahil Rehan from Facebook, who is going to be talking about how we've built up a trusted computing platform.
Thanks, Ryan. Wow, it's bright. All right, people, one more talk before the break, so hang in there. I'm going to try to go fast, make this less boring than it actually is. So I'm going to talk to you a little bit about trusted computing. All that stuff is how you can get in touch with me if you're super passionate about this stuff. So what are we going to talk about today? We're going to talk about why you need trusted infrastructure. And by infrastructure, I mean basically all the stuff that's running inside of your data centers. What do we mean by trusted infrastructure? How can we build that at scale? And then later on in the talk, we're going to talk about sort of what are some of the more gnarly problems and unsolved problems, and what can we do about them. So just to start the story off, this is kind of what they show you in the movies for what your data center or your infrastructure looks like, right? There's some yellow guys that are good. There's some orange guys that are bad. There's a red firewall. There's all your servers over there on the right-hand side. Everything's good. Bad guys are outside. Servers are inside. You know, Sandra Bullock, the net, all good. We all know that's not true, right? I mean, we're more sophisticated than that. So this is what we think is really going on. So we have, you know, some of the bad guys, we know they're going to try to get in. We have all these fancy green lines. They're like lasers, Mission Impossible. We have our OS hardening, SE Linux. We might have some app containers. That stuff's fancy these days. You know, all kinds of auditing and monitoring tools. You might even throw in some, you know, whiz-bangy machine learning stuff in there. Some of it actually works. Hey, really, there's a lot of snake oil out there, but some of it actually works. So here's the problem with all of this, right? The problem is that most of the stuff that happens at the application layer or above. And very few things are looking at the syscall API or below. And unfortunately, that's a really juicy target area for attackers because that's a great place for persistence and for avoiding detection. So yeah, danger lurks below the syscall boundary. And so there's a lot of things that are running on your system that most people don't think about. BIOS, firmware, the SMM handler, which is like the super privileged ring -1 code that nothing can read, but it has read access to every other piece of memory on the system. And these things are very hard to detect, and they may be impossible, nearly impossible to eliminate. So, you know, wiping your hard drive is not going to get rid of a BIOS malware. And if your hard drive firmware is infected, then you basically need to throw away your hard drive. OK, so now you take this and you take your data center for a large company and you put tens of thousands or hundreds of thousands of servers in there, and you start to see that the problem starts to get really gnarly, right? When you look at this big data center with racks full of servers and you're like, how do I know whether this server came up in a good state or not, whether its BIOS is infected or not? Who's going to go and check all of these things? OK, so before we get into sort of the good news part of this, I just want to say that sometimes people will be like, oh, you know, this doesn't happen in real life. And to some extent, that's true. And to some extent, that's just wishful thinking. These things do happen. It's totally possible. There's the Thunderstrike exploit, which would basically override your BIOS firmware by attaching a PCI device to your Thunderbolt cable. In 2015, Kaspersky Labs exposed the Equation drug, which is basically hard drive malware, which is rumored to be from the Equation group, which is backed by the NSA. There's the Light Eater exploit that the guys at Legbacore put out, which can theoretically infect millions of BIOSes and is undetectable. And most recently, Cisco Rombon attack, in which once people were able to compromise the credentials on a Cisco router, they were able to reflash the firmware on those routers. And Cisco didn't really talk about what exactly those people were able to do, but presumably you can reroute packets, you can steal data, you can do whatever you want at that point. OK, so how do we build trusted infrastructure at scale? So the basic idea here is that you want to secure the platform. You want to know that the platform's in a good, clean state before you start using it. And so the way we do that is we want a way to be able to remotely query a server for its state, validate that state against some set of locally stored whitelists, and this will tell us whether or not this platform's in a good state. It does not tell you whether or not the platform is still in a good state after it has started running. So this is just a boot time protection. Cool. So all of this is basically based on using an x86 CPU with Intel TXT support and a chip called the Trusted Platform Module. You don't have to use Intel CPUs. ARM has an equivalent technology called TrustZone, but I'm just going to use that for purposes of illustration. And so the idea here is that the root of trust, the reason that you start trusting anything is in the CPU. These CPUs have a public key that's burned into them at manufacturing, and that public key signs a piece of code that initiates the measurement process. The CPU will verify that piece of code before it starts executing it. So now you trust this piece of code, and the idea here, where you see the stack on the left or on your right, is that each step will compute a hash of the next component that's going to run and store it in the TPM before it transfers control to that component. Now, the nice thing about a TPM is that writes are append only, which means that the new value is never stored as itself. It's always appended to the old value, and the hash is computed over that whole value, constructing a hash chain, which means that an attacker can't just replace the value, the old value, with the value that they would like it to be and escape detection. The other nice property of a TPM is that every TPM has a unique public-private key pair burned into it at manufacturing. And so you can remotely query the TPM for this list of hash values that are stored in the TPM, and it will return this to you signed by that key. So you can say provably that this set of values has indeed come from the TPM and not from some attacker. So the basic idea is that the CPU starts up, you trust the CPU, hopefully you trust Intel. They have a piece of code that measures your BIOS measures your option ROMs. Then at a later point, you start the process for measurement for more of the runtime components, which include your trusted boot module, which is a technicality for Intel TXT, so we'll just skip over it. Your platform config, the kernel, your OS config, et cetera. And at each step, the idea is that the component, let's say your kernel is being measured by a tboot, and then control is transferred to your kernel, then your kernel measures the init RD, and then transfers control to the init RD. So you could run something malicious, but you can always detect after the fact that it was malicious. It can't evade detection. So this is just a quick view of what it looks like. In a TPM, there are 24 PCRs. Each PCR usually has some predefined meaning. 0 through 7 are sort of the static firmware BIOS kind of state of the system. And the other ones are there for software to play with. You can see there's an OS measurement in kernel 18. That's the kernel hash. You can also see further up there's the kernel command line. That's also being measured. PCR 0 has the BIOS measurement in it. And they're all basically hash values. So unless you map them to something textual, it doesn't make much sense. OK, so how do you do this at scale? So the basic idea is that you take all of this and you put it together so that you can manage this huge data center full of servers. So let's say you have a configuration management system, right? And the objective of that configuration management system is to push out some stuff to your servers. Now, the way you want to set this up is that you have an attestation service, and the job of the attestation service is to look at a particular server and tell the configuration management service whether it's in a good state or not. So it needs to know already what's the definition of a good state. And this is where we bring in the concept of a whitelist. So you have a build system. It produces a build as an output. That build needs to be sent to this attestation service to be whitelisted to say that this is a blessed build, and we accept this. Right? And then you can send the same thing to your configuration management system. So before it tries to use a server, it's going to go to the attestation service and be like, hey, should I start provisioning this with, I don't know, whatever, Chef, Puppet, putting my keys here, putting my secrets there? The attestation service is going to go query the TPM on that server, get the list of hash values back, compare it with what it got from the build output, and be like, huh, kernel looks good, init RD looks good, root file system looks good, BIOS looks good. OK. So this server is trusted, and it tells your configuration management system that, and then you can go ahead and proceed with using that server. So that's all good. You're done, right? Game over. Let's go home. Not quite so fast. So this is a section where I'm going to talk about some of the more complicated things that you need to think about when you're thinking about how to trust your server, or what other components can be malicious or untrusted in there. So top of the list is malicious devices, right? PCI devices have direct access to memory. You can DMA anywhere, which means a device can basically read any piece of memory, including a piece of memory that has a secret in it. So you want to do something like use an IOMMU to restrict the range of memory that the PCI device can access. Driver hardening is another big one. Operating systems operate under the assumption that the device is trusted. So if you have a malicious device or it's been flashed with malicious firmware, the driver's not expecting that. So they're not checking the values that the device is telling them about or the memory ranges the device is telling them about. And they'll happily go and read something from someplace they're not supposed to, as long as the kernel gives them access to it. BIOS and SMM handlers are another biggie. The thing with the BIOS is that usually it comes pre-installed on your machine, and most people don't have access to the source code. So while you can compute a hash of the BIOS, it's really an opaque value. So what you really need is access to the source code to see how many zero-day vulnerabilities are in there. And BIOSes are notorious for this. The thing I mentioned in the beginning about the light eater attack, which can infect millions of BIOSes, one of the reasons it's that effective is because basically everybody builds off of the same BIOS DDKs. And so, the thing is that they don't bother to go and look at what's in the DDK. So if there's one exploit that works on one of the BIOSes, it probably works on most of them. SMM is another beautiful thing that you can thank Intel for. Hopefully there are no Intel reps in here. It's ring -1 code. It's super privileged. The kernel cannot see what's inside of the SMM handler, but the SMM handler can see everything outside of itself. So if you get access to the SMM handler, that's like you're in heaven. That's like attacker's heaven. Firmware updates are also another biggie. So you have multiple devices. They all have firmware. Very few cases do vendors actually have signature checks for firmware updates. Most of them don't have any notion of rollback protection. If they do tell you that they have signatures, go and check those signatures. It might be the case that they have the private key and the public key in the signed image. So don't take their word for it. Remote access, I'm not going to talk too much about it, but for those of you that use servers in data centers, you know that you can get a remote console, you can remotely power on, power off. That's because basically there's another small computer sitting there that never goes off, that takes your commands and turns the servers on and off. And that's called a BMC controller. And that's basically got its own firmware, it's got its own version of Linux running over there. Same problems apply. Can you flash it? Can you override it? Can you do a rollback attack? Blah, blah, blah. So you heard of Sony Pictures, right? And how like the attackers came and instead of stealing anything, they just destroyed all the hard drives and tried to put Sony out of business. So imagine that in a world where you're doing firmware attacks. You wipe the hard drives, you wipe the BIOS, you wipe the BMC controller's flash, and that's it. Basically, the only way for you to recover this server now is to physically send a tech into the data center, pull the server out of the rack, and reflash the BMC controller. So the fact that the servers are so vulnerable and your business can basically be shut down is a scary thought that doesn't occur to most people. Okay, real quick, this used to be about protecting secrets in memory, but Intel, again, and I don't shill for Intel, but they're coming out with this really cool technology called SGX, which will basically allow you to have encrypted main memory. So you can create an application container, and the contents of that container are always encrypted in main memory, and they're only decrypted in cache. And the system, the hardware guarantees that nothing outside of the container can see the memory that's stored inside the container. So it's basically invisible to the rest of the system. So this is going to be a great place to put private keys, secrets, other things. Also, these containers have the nice property they can be remotely attested, so it can be running on a server somewhere. You can talk to it, prove that it's running the code it claims, and then only then give it the secret. Right? So one of the places I feel like this could be really valuable is for agents that you're running on your system that you don't want hacked. So Carbon Black people, I'm looking at you. Anytime now. Okay. So black belt paranoia. So if you thought that was as bad as it can get, well, think again. So this is a server, right? This is what they look like. I don't know how many people in here have actually opened up a server from a rack. But generally there's some parts there, and it's very hard to tell what parts belong there and what parts shouldn't be there, right? So as it turns out, there's actually something in this board that shouldn't be here, and it's this little thing. And that little thing is a PCI device that masquerades as a network card and can be programmed remotely to exfiltrate data. I can basically send it commands and say, I want physical address 1 megabyte to 1 gigabyte. And I want you to copy that out and send it to me. And it will do that. And there's basically no way for you to know that from a casual inspection, right? And I don't want this portion of the talk to just be about like scaring the daylights out of you. So I'll tell you what people are doing to deal with this, right? Or trying to do to deal with this. People talk about X-raying every server that comes through customs and using image recognition technology to compare it with an X-ray of a known good server to see if somebody's put something in there, right? The same thing that I talk about with a card, you can actually also do with a chip. And again, you'll be like, nobody cares about this, nobody worries about this. There's a company out there that claims to take super high resolution photographs to the extent that they can detect differences in finish between one manufactured IC and another, just from the surface finish. And they're like, no two ICs will look the same under this resolution of photograph. Okay, other stuff that could be bad, right? So, there's this guy, Snowden, he did this bad stuff, he has to hide somewhere. The thing that people don't realize is that what Snowden really did was he put out the cookbook for the bad guys, right? Before Snowden, people were like, oh, yeah, theoretically, if you had a USB adapter and you could put in a wireless card into that, then theoretically, you could exfiltrate some data. And what Snowden did was show everybody that, yeah, this is actually possible. So right now, there's somebody over there looking up some manufacturer in China being like, hey, can you build me one of these? So next time you go to a conference and you're like, oh, I need to plug my phone over there, think twice. Okay, one more. So where does all this bring us, right? Basically, there's all these components that are untrusted around the system, but if you start looking at the board of the system itself, right, and this is really like, peeling an onion. You start on the outside and you're like, okay, is my kernel legit? Is my BIOS legit? Are their drivers legit? Are their devices legit? Okay, fine, so far so good. And then you come and you're like, okay, what's on the motherboard itself? And it turns out the motherboard is just one big network. It's all of these things that are connected to each other with buses. There's PCI buses in there, there's an SM bus in there, there's an LPC bus connecting the TPM. Most of these buses are obviously unencrypted and unauthenticated. So if you find a way to put in a malicious device over there, you can read data, you can reprogram the TPM, you can bypass everything that we've been talking about so far. So one way to think about security from the ground up, and that's kind of what I'm getting at here, is that we really need to take a step back and be like, okay, what do we trust? Why do we trust it? Where does that trust begin, right? Let's say you trust your CPU, right? How do you build a system to trust other components starting from just that CPU? How do you make sure that all the other firmware that's on your system is trusted, that your devices are trusted, that you're talking to authenticated RAM and not to something that's like NVRAM or battery-backed RAM that's like writing out your secret somewhere else? And we need to start thinking about it as sort of systems designers in that way. So kind of to wrap it up, I feel like this is going to be the next frontier for infrastructure security. And the solutions are complicated. There's no one-stop solution. There's many different components that need to be dealt with. You need to deal with your vendors, firmware, hardware, and a lot of software needs to be built. It's going to take a long time to get to where you want to go, particularly because of all of the different entities that you need to deal with, not least of which requiring specific hardware. And there's a lot of software to be built. Even just to do what we talked about, just to do remote attestation, there's really very few tools out there. There's enough tools that'll get you to the point where you can read the hash value out of the TPM, right? And you can look at a list of hash values. But that's not an integrated solution, right? Being able to integrate it with a build system, integrate it with whitelist, being able to temporarily whitelist something, being able to blacklist something, allow some servers through for testing, none of these kind of mechanisms exist. So there's a lot of opportunity here for building software to help create a trusted infrastructure. All right, that's it. You all are off the hook, and we can go to break. Thank you.